All right. And we are back for the last of these lectures on limits. Let me actually maybe move this. No, the other way. Just that part of the board. Perfect. Okay. All right. So this time you'll notice I don't have the book projected up there. I'm going to use some problems out of the book. Again, just kind of nice fodder. But I want to, this time, since we're going to be talking about the limits of these functions when you don't see a graph, I want to just let's uh, let's just kind of write these functions up there and kind of talk through what we're looking at. So first off, let me get grab. Doesn't really matter. First off, let's say I wanted you to find the limits x approaches, it doesn't matter, say 4 of 2x minus 3, something like this, that function. Again, before, so in some ways, notice that we're literally like starting all the way back to the beginning of this total lecture. So we're back to having a linear function, and I want the limit as x approaches some value there. We talked about in the last part of the lecture that with rational functions, trig functions, etc., you need to think back to what you already know about them. What you already know what these graphs look like. Well, it ends up then to sort evaluating the limits of something like this when you're not given the graph. Again, a bit like I said in the last lecture, you still need the graph. You don't necessarily need the graph in front of you, but you need to think back to what this function in general looks like so that you can figure out what we're really concerned about is this function continuous? So this function, so the idea is to think about just sort of the general graph of this function. It's a linear function, so what does the graph look like? But it looks like a line. Is a line continuous? Any line, no matter how it's pitched, where it's placed on the XY axis, is a line continuous? What do you guys think? Good. So if you're thinking of that picture of a line, unless it's like, well, no, you're not even, yeah, a line's continuous. Again, to be continuous, that means the limit has to exist at every point, the point has to exist, and those values have to match. And for a line, that always works, right? So figuring out whether the function you're looking at is continuous actually ends up being kind of our, I won't call it a shortcut, but it ends up being the first thing that we need to think through because if it's continuous, again, think about what continuous means. Continuous means the limit exists and we're trying to find the limit. So the first thing is it tells you that the limit exists. It means that the point exists, and it means that the limit and the point matches. So if the function is continuous, that tells us then that whatever the y value is actually what the limit value is. So basically it tells us our shortcut for finding the limit is just plugging the number in. But again, that only works if the function is continuous because we know the definition of continuous. The idea of continuous is that the limit exists, the y value exists, and those match each other. That's the key, the fact that they match each other. So that allows that shortcut. So we're gonna, when we're trying to find out the limit of these, the first thing is to figure out whether it's continuous. If it is continuous, that means we can plug it in and we're great. So here, we can plug this in, 2 times 4 minus 3, and we're great. So that equals 5. So the limit as x approaches 4 here is 5. Again, it's only because it's continuous. And to analyze that, you honestly just need a picture of the graph in your head, the general picture of the graph. Good. So as long as they're continuous, easy enough, honestly. So let me give you a couple along those lines. Let's see. That's that. Or it really doesn't matter. What else do I want to do here? Throw something in like that. Oh, yeah, we got the properties of. Blah, blah, okay. That's fine enough. Sure. Okay, let's just throw up one. So, let's do the limit. So x approaches, say -3. Nah. Or the square root of x plus 8. Figure that out. Let's do limit. Let's make this. Use 4x plus 3x 5. Maybe it's x approaches. Slightly interesting there. X approaches 2, something like that. So, So actually, I'll have you guys work those very quick. Oh, sorry, let's move on. The responses. Um, so have you guys work those four really quick? So go ahead and pause on your side. I'll pause on my side. We'll see what we get. All right, so we are back. Ooh. So let's say we're looking at conversion. I'm sorry delivering right now. No, sorry. Maybe for Dustin, we got the name on. All right, looking at number 2, so we have a square root function, radical function. So again, the question is, in your mind, go and kind of find general form of that function graph. Is it contiguous? And yeah, especially within its, within its domain. So as long as we're within the domain, it is definitely continuous. It's a solid line. There's no jumps, there's no breaks, there's no discontinuities. The limit exists. In this case, we square roots again, so kind of like we did on a previous problem. The square root graph normally, if this is square root of x, that normally looks like the following, right? So normally the domain is 0 to infinity. The plus 8 is going to move this to the left. It's now my domain. It's -8 to infinity. So as long as I'm somewhere between -8 and infinity, actually including -8, I'm good. It is a continuous function. The limit exists. the y value exists and they match each other. Good. That means I can go ahead and just plug this in. -3 plus 8 and -3 plus 8 is 5. So my limit there is square root of 5, the y value. Good. What does the graph of the function number 3 look like? Good. That's a polynomial. That's some wiggly kind of mountain and valleys curve thing. Kind of like an S, but with mountains and curves. Nonetheless, thinking about that graph, there from -infinity to infinity, that thing is continuous. No breaks, no jumps, no holes in the graph, no vertical asymptotes, etc. So I can just plug this in and get to calculate. 2 cubed is 4 times 2 plus 3 times 2 minus 5. And what, 8? And that's actually 1. And there we go. Good. Now again, natural log or log graph. Again, if this was natural log of x, graph looks like this roughly. This one does have a vertical asymptote. And -2 means we're to the right 2, actually. So actually, let us so this graph is going to look roughly like 1, 2. So there'll be a vertical asymptote at x equals 2. And then it looks roughly like this. But within its domain, so from 2, not including 2, but 2 to infinity, as long as we're within its domain, this is a continuous graph. So there's no discontinuities east of 2, right of 2. So as long as we're there, the limit exists, the y value exists, and they match. So again, that means 4 is right of 2, it is east of 2, so we can plug it in and go. Natural log of 4 minus 2 is natural log of 2, so that would be your limit there. And then 5, what about sine x? What would that graph look like? Good. So sine is your pretty famous now. Hopefully it is famous for you after you take the pre-calc class, or famous kind of wave, circular function. And this 1/3 in front, that's being multiplied in front, so that's going to shrink the graph vertically. So the graph of this would roughly look like, let's say that's 1/3 and that's -1/3. The graph of this roughly looks like so. There, just keeps going. But again, you think about that graph, is it continuous? Indeed, everywhere. The limit exists, the y value exists, and they match that. There's no sudden jumps in the graph, there's no holes in the graph, there's no etc. So that means I can just plug this in and go. So 1/3 sine of pi over 4, and what is the sine of pi over 4? Okay, so this should be 1/3 times now the square root of 2 over 2. Again, a note, as you guys probably, as you saw in the pre-calc class, or you should have saw in the pre-calc class, I want exact answers, which means I don't want decimals. I want the square roots. And if you can't resolve the square roots, they should stay in the problems. They should stay in your answer. I want exact answers, not decimal problems. So this is going to be the square root of 2 over 6, and there we go. The limit is x approaches pi over 4, and 1/3 sine x is square root of 2 over 6. So all of this is good enough. So again, the point here is if you know the function is continuous or continuous within the domain that you're looking at, then you substitute actually finding the limit for just plugging in the number and finding the y value, because you know they match. So then the more interesting part of this is what happens when Again, so the last video we were looking at finding where a function is not continuous. So when it's not continuous, so when there's a discontinuity, it doesn't necessarily mean that the limit doesn't exist. So again, continuous means the limit exists, the y value exists, and they match. To not be continuous, you just need one of those, what do you call it? One of those qualifications to fail. So for instance, you could have, to not be continuous, to have a discontinuity, the limit could exist and the y value could exist. They just don't match each other. We saw that with several graphs on that last video. Or the y value couldn't exist. We saw that with a couple graphs too. There's several ways to have discontinuities that you just have to take down one of those qualifications, and it doesn't have to be that the limit doesn't exist. So if something's not continuous, the limit could still exist. In fact, we saw some examples like that as well. And we saw some visual examples. So now we're going to look at, so the rest of this is we're going to look at some functions that have discontinuities, and we're going to try to find the limit at the discontinuity, because it is still possible that that limit exists. That's where our work really lies. So let me grab some examples. Grab some fodder. We'll get back to that. This is where we really got to do some. All right, give me a second. I'll pause. Let me just kind of gather all the problems I want to look at first before we jump into it. Oh, I didn't unpause. Okay, sorry guys. I didn't realize I didn't unpause it. All right. So let me explain kind of what I did here. So you're looking for the limit as x approaches -3 of x squared plus x minus 6 over x squared minus 9. So what I was saying here is, this is why I shouldn't actually. So the first thing that I was saying about this is, oh no, when I come back, we already talked about the 0 over 0. So when we're coming back, you guys are coming back from factoring. So the factoring that you get here is x plus 3 times x minus 2 over x plus 3 times x minus 3. So what I was saying here, think about factoring is to me kind of like a cheat code, like a secret code. You kind of get to see the insides of what's happening in this polynomial. And so we were getting 0 over 0 when we plug in -3, but the reason why we're getting that is because -3 plus 3, these two factors here that match, -3 plus 3 is 0. 0 times anything is 0. So once you get the 0 out of one factor, it's Type-Losch, it's 0 the rest of the way. So the reason we're getting 0 over 0 is actually because of these two factors that match each other. So what happens if we cancel those factors out? So in terms of just how fractions work, I can cancel out common factors. When fractions, so like, when you have a numbered fraction, 6 over 8, that's equal to 3/4, right? It's the same values, it's just canceling out a 2, top and bottom. The difference here is when you cancel out the x plus 3 and x plus 3 here, so it leaves you with x minus 2 over x minus 3. What that does, notice now if you plug in a -3, you're not getting 0 over 0, because what that does, again, initially, this gives me a graph with an open circle at -3. I get 0 over 0. By canceling out those common factors, you're taking out what's causing the 0/0. So what it does is it literally fills in that open circle with a point. But like, again, in the last lecture, we were talking about when you have a removable discontinuity, that's what you want. You want to be able to, that's the point of removable discontinuities. We're saying you can fill it in with a point that would have the same y value as the open circle that we have there, and therefore the limit of the function. So filling in that open circle just tells us what the y value is, which means that tells us the limit. So again, by canceling out these common factors, what you get is a graph, is a function that is almost the same as the original, except for that open circle is filled in with the dots. But that means that this is continuous. So I can plug in -3, and that tells me the y value at that dot, which tells me the limit at that open circle. So I went ahead and plugged in the -3. And what you get here is 5/6. So the limit is x approaches to -3 on this original function is 5/6. That's the y value at that open circle. All right, good stuff. So then I'll have you guys play the same game with this. So we want the limit is x approaches 4 of x minus 4 over x squared minus 16. Again, you have a rational function. Again, plug in 4, you're going to see 0/0. So you're going to see a removable discontinuity in the open circle. So you can play the same game and get the y value there, get the limits. All right, so pause on your side, I'll pause on my side, and we'll come back and finish that up. Just for your curiosity, if you do, you plug in 4, you get 0/0. So we know it's a hole in the graph. So the factoring is pretty easy on this one. X plus 4 times x minus 4 on the bottom. So then we're going to cancel out the common factor so that we can assess the real limit there. So x minus 4's cancel. We end up with 1 over x plus 4. Then I'm going to plug in the 4 from there. So to be accurate, I should be writing limits. I should be saying limit of and blah, blah, blah here. So I'll take some shortcuts in my writings, but limit of x plus, as x approaches 4, of now 1 over x plus 4. And so what we end up with is 1/8, and that is our limits. All right, good stuff. All right, let's look at another problem where we really got to do some algebra to kind of figure out, again, we have a discontinuity and we need some algebra to really figure things out. Let's look at something like this. Again, we'll do limit as x approaches 4. But this time it's going to be something like this. So the square roots of maybe x plus 5. Sure. Minus 3, and this is over x minus 4. Now the surprise on this is, again, if you plug in 4 here, you do get 0/0, which isn't as immediately clear. I think looking at this, you would figure that the top would be some number. The bottom is definitely 0, but the top would be some other number. But surprisingly, square root 4 plus 5 is 9, so you're going to end up with 3 minus 3 on the top. 4 minus 4 on the bottom, and indeed this is 0/0, which is a nice, beautiful, removable discontinuity. That's a nice open circle. So again, you got to be able to recognize what this situation is, which is why I would continue to have this written up here. But easy enough. So that's a hole in the graph, which means there is a limit there. but we can't calculate it by just plugging in the 4, right? At least to what we have there. Now, the difference here between maybe here and questions 6 and 7 that I gave you is I can't go and factor this. This isn't a polynomial. So that's really the difference here is in the bottom of this grade, that's easy enough, but the top is definitely not a polynomial. So this factoring tool, this technique, this skill that we have, fortunately doesn't do us anything. So what do we do with this? How do we sort of, in some ways, what we're doing, not just with this, but what we're doing with essentially all of these problems is when you end up with that 0/0, we have to have some way algebraically to transform the function into something that is, that's transform the function into something where we can actually plug the 4 in and not get 0/0. Something equivalent, something that's the same, but it's gonna have a dot at that open circle. You're actually gonna get a y value there. So if it's polynomial over common factor, and we cancel out common factors, easy. But if we're dealing with the square roots, then what we're gonna do is, again, in college algebra, you guys, and in pre-cal, you guys also did this thing called rationalizing the denominator. It actually doesn't have to be a denominator, but basically when we saw square roots, we would rationalize them away. And so when we did it in the college algebra class or pre-cal class, we were actually doing it. So they would have you do it basically just to write the answer the correct way. Now, if your teacher never told you, that actually didn't mean anything. Rationalizing the denominator doesn't, like that, the second version of it isn't more correct than the first version. It's completely fine to have square roots and numerators, denominators, wherever you want. That's all good. Mathematically, that's completely full. There's no difference. So in college algebra class, pre-calc class, when you were rationalizing the denominator, it was really just an aesthetics thing. The book didn't want to see square roots in certain places. Mathematically, that doesn't matter. However, what they were really doing was that technique ends up being instrumental. It ends up being the tool that we need to basically, again, transform this into something where we don't have the open circle and we can plug the 4 in. So that technique, really what they're trying to get you to do is honestly just play with that technique. Get good at that technique. So we're gonna use that technique here. And notice my square root is in the numerator, not the denominator. That technique works on either side, whether the square root's in the denominator or numerator. And that technique, so again, they called it rationalizing the numerator, denominator, rationalizing the radical. The idea was wherever you see the square root, we wanted to, if the square root's by itself, you just multiply by what that square root is. But in general, what you're going to see, especially a lot in this class, is you're going to see an expression, a setup like this, where you have a square root plus or minus a number. And to rationalize it, you need to multiply it by the same two pieces, but with an opposite sign in between. We need to multiply this top now by the square root of x plus 5 plus 3. We do this because by having the -3 and +3, we get like terms that cancel out. And so you basically end up losing the terms that have the square root in it and just ending up with a polynomial from there with just x terms and numbers. So it's a trick. So the thing about it too is, again, like I said, it's a tool. It's really just a trick for eliminating the square root terms and whatever side that they started out with. So that I do want to emphasize. It's just a trick. It's a nice little trick. We're going to multiply this through in your distribution, and all your square root terms are going to go away, and you're going to be left with some nice clean terms. But if I'm going to do this, if I'm multiplying the top of a fraction by something, I have to multiply the bottom by the same thing to keep the same value for the fraction. So we multiply the top and the bottom. So what I'm going to do here, because I've seen this done before and I sort of know algebraically what's going to come up, I'm actually not really going to multiply at the bottom. And then, by the way, see, the bottom looks horrible. So if you have to multiply at the bottom, what you're doing is literally You have to multiply x by each of these terms and 4 by each of these terms. And nothing really actually multiplies there. Also, there's no like terms, so you end up with a gangly looking horrible thing, horrible kind of mix of a polynomial square root things on the bottom. So I'm actually not gonna multiply out the bottom. Just gonna keep it as x minus 4 times the square roots of x plus 5 plus 3. But the top I am gonna multiply out because things work out nicely and simplify. So literally, I'm just gonna do distribution. So we're gonna do the square root of x plus 5 times the square root of x plus 5. If you multiply the square root of something by itself, it just leaves you with what's under whatever's under the square root. So square root of x plus 5 square root of x plus 5 is x plus 5. And then I'm going to do the square root of x plus 5 times 3. And that 3 can't multiply by anything inside of that, so we just end up with 3 square roots of x plus 5. So just this gangly, kind of horrible looking thing. That is half of my distribution. Now I'm going to go back with the -3 and multiply through. So -3 times square root of x plus 5 is -3 square root of x plus 5. And then -3 times 3 is -9. And like I said, this is multiplying by the same thing but different sign in between the two pieces. It's just a trick, because notice that forces these middle two terms to cancel each other out. Literally, it's just a game, but it's a nice little strategy toward it. Forces the middle to cancel out. And notice what happens from here. So what you're left with on top is x plus 5 minus 9. What is x plus 5 minus 9? That is x minus 4. Notice how that accidentally, coincidentally, strangely matches one of your factors in the bottom. So ultimately, that should happen. So again, the 0 over 0 thing. So ultimately, what we're saying, it happens when factors match top and bottom. And we didn't do any factoring on 8 to get there, but by multiplying by the rationalized version of the square root there, or they also sometimes call it the conjugate, you end up with the factor you need to cancel. And it really, as I say, magically, it's not magic, but it kind of is. It's actually kind of crazy how well that works out. But it does, and I want you to trust that it works out, because honestly, this line here, this work, looks crazy. It looks like we're not getting anywhere and things are just getting worse. And suddenly, things are actually much better, and we are getting something. So my x minus 4 is canceled. So now what I'm looking at is the limits as x approaches 4, simply 1 over the square root of x plus 5 plus 3. So this will be the same function as the original, except for that open circle will have a dot. Now I can plug it in and get a value. Plugging that in, it looks like we have 1 over square root of 4 plus 5, which is a 9. Square root of 9 is 3. 3 plus 3 is 6. So grand total, my limit here is 1/6. And this is the other, I would say, just kind of special type of problem. I won't even say special type of problem, just special algebra skill that you have to pay attention to. It gets used in this section a lot. But you'll see as we go through the course, both of these skills. So factoring, canceling out common factors, and then multiplying by the conjugate, so rationalizing the denominator, numerator, and then seeing which can cancel and working from there. Those two skills get used in a ton of problems as we go forward. So this little bit of algebra work, if you feel like you didn't master it in your previous class, we're going to do a lot of it. We're going to do enough of it that you'll definitely have it mastered, but make that your goal. Master this technique. Don't just kind of get by or do the problem or do enough to get the homework done. master the technique, because we're gonna keep doing it a lot and you need it mastered. You don't need to be able to do it, you need to really have it thoroughly, you need to thoroughly know it, and thoroughly be able to play it. Uh, So the limit is 1/6 there. Um, so you'll see some problems like that. It is getting late on my side, so I'm not saying we still have a little bit to do, but it's getting late on my side, so I normally would give you another problem to play with. But I need to get my son some dinner very soon. So let's see what else we have to look at here. Mm, 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 mm. I think what we have left. So like I said, what we're drifting into here is some problems where when you plug the number in, you get some discontinuity, and we want to figure out what to do with those. We're gonna have two essentially special situations here. So some sort of rational function where you're getting a hole in the graph, which is coming from a common factor, and a sort of rational function with some square roots in it, and getting 0/0, and so rationalizing the numerator in space or whatever, wherever it is, that's our way of dealing with that. There's also, so at the end of this section, so this section is 2.3, they talk about, what do you call it, they talk about what's called the squeeze theorem. So unfortunately, when I teach this class, I can't teach it as theoretically as I would love to. The squeeze theorem is actually crazy interesting, really useful in a lot of higher level theoretical mathematics. And also just makes a ton of really awesome sense. However, we don't have time to sort of explore the theory side of it and why it makes so much sense for things. But what I can tell you is some of the results from the squeeze theorem. So the results from the squeeze theorem give us basically, I'm literally gonna write for you some certain limits for a couple different functions and situations where you end up with 0/0, but mostly having to do with trig functions. We call transit. So there is actually also a great video that you can click on in the book on this section on squeeze theorem. Like I said, it's actually really curious, cool, and interesting, and it makes a ton of sense, but we just don't have the time to talk it all the way through. There's also another one of the sections, I think 2.4, something called the intermediate value theorem, which I will reference later. We'll get to some stuff with derivatives. But the intermediate value theorem is also another, it's actually, that one's a very basic common sense thing and kind of makes sense. But again, for sake of time, I just don't have the time to sort of delve into it. It makes a ton of sense, but it still requires setup. So if you get a chance in 2.4, just kind of read through that. There probably is a video on it as well. But from the squeeze theorem, we get some certain limits that we suddenly know the value of. So I want to kind of highlight these. Well, I don't want to call it squeeze theorem though, so we'll just, these are some special limits. And these special limits are, so the limit as x approaches 0 of sine of x over x. So notice what I'm doing here is, even if you knew nothing about the squeeze theorem, what I'm doing is I'm setting up a situation, again, another fraction, where I end up with 0 over 0. The sine of 0 is 0, and dividing that by 0 gives you 0 over 0. So the interesting thing about this, though, is this resists, so for the last couple problems, we had sort of some special algebraic ways to deal with this. This resists a lot of special algebraic ways to deal with this. But using the squeeze theorem, we can prove actually that the limit of this, and let me make sure I get this right, because limit of this is 1. There is a hole in the graph, but you can use the squeeze theorem to show that the y value of that hole in the graph actually has to be 1. So this setup, sine of x over x, the limit as x approaches 0, this very specifically is basically a limit you're going to have to memorize because it will then become useful in a lot of our, not just the problems in this section, but a lot of our problems in this class. There is a similar limit, so the limit is x approaches 0, 0. 1 minus cosine of x over x. Notice that this is a similar situation. Cosine of 0 is 1. 1 minus 1 is 0, divided by 0. So in some ways, these two are very similar in that they're talking about basically a trig function being divided by its own variable, essentially. This equals 0. So the limit on that, make sure I get that right, is 0. Again, this would resist any algebraic technique of kind of resolving what's going on. You can't multiply it by 1 plus cosine x and then do some special things there, which is what you think maybe you'd be able to do. And then again, this one is even worse because I don't have anything to play with there. I just have a sine on top and an x on the bottom. So I don't have anything to factor, no plus or minuses to play with. And then the final one, the limit as x approaches, yeah, it should be 0. Yes, 1 plus x. Limit as x approaches 0, 1 plus x to the 1 over x power. So this is a more interesting one than maybe the other two. I mean, maybe they're all interesting. But this is interesting because, so again, this has nothing to do now with a polynomial, a rational function. It's not a trig function. It's an exponential function, but it's a weird one because you're raising things not just like some solid power, but 1 over whatever x is. So when x is 5, you're raising it to the 1/5 power. When it's 6, 1/6. Problem here is, what in the world do I do with raising it to 1 over 0? Because 1 over 0 does not exist. That's not a calculation. But again, if you graph this, you would see a trend in behavior coming from the negative side and the positive side there. Just at 0, there would be a hole in the graph because you couldn't really identify what that is because 1 over 0 doesn't exist. And the limit for this actually ends up being the number e, the natural number e. And so this limits, again, algebra techniques wouldn't get you there, but the squeeze theorem does it for you. But the other interesting thing about this is that this limit is the reason why we'll look at this a little later on in some detail, maybe not all detail, is the reason why every exponential function can be basically related back or changed back to the to the e to the x. So you may have seen that or heard your teacher comment on that before when you looked at exponential functions in your college algebra class, that you can have any base you want to, but the interesting thing is everything can be related back to e raised to a power. And the reason for that ends up having to do something with the derivative and this one. So we'll get there later. So these three special limits, again, what I'm basically saying is you have to memorize them because there's not an algebraic way to get them. Squeeze theorem gets you there. Squeeze theorem is a logical proof. It's not actually algebra. But you have to have these memorized. And at least immediately, we memorize them so that we can do something like the following. Let me find these problems. Blah, 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 blah. Let's start with something like this. 8, so let's make this 9. We have the limit. X approaches 0. Sin x over 5x. So just a slight alteration on this, on the actual special limit itself. Make sure I wrote it right. And the key here is to recognize that you have that nugget, you have that special limit basically written into this. In fact, I mean, just algebraically, I literally can rewrite this as 1/5 times sine x over x. Which means I know the limit of this part, right? So what's the limit of this part? That's 1. And so then all I got to do is multiply that 1 times 1/5, and I get my answer. So limits have some patterns, some properties. One of those patterns is if you know the limit of one thing and you want the limit of some number multiplied by that thing, then you just multiply the number by that. There's basically another way to think about it. There's no x here. There's no x to plug in. So this is just a constant being multiplied by this. Sizing it down. Like you've seen again with transformations of functions. So this is going to be 1/5 times 1, which is indeed 1/5. So the limit of that is 1/5. But again, if you don't have this memorized, then there's no algebraic way to force to work yourself out of this situation, out of the 0 over 0 that you find there. Also might be to see something like this. Maybe the limit as x approaches 0. Let's do sine squared x over x. And again, the two keys here. The key here is knowing this special limit, but also knowing that then we can start doing some basic algebra to sort of factor things apart and break this apart into pieces. So this is going to be the limit as x approaches 0. What I'm going to do here, I have sine squared, so I'm going to break this into sine x times sine of x. And then I still have divided by x, so I can go on either of them. And then notice that, so basically notice my basic strategy here with, once I know these special limits, especially with the trig functions, is I'm just going to break it apart into pieces that I can deal with, that I know each limit separately. Because again, one of my patterns with limits says that if I want the limit as x approaches 0 of this thing times this thing, if I know the limit for the first thing and I know the limit for the second thing, then the multiplication follows. I just multiply the two pieces together. So what is the limit as x approaches 0 of this first part? Good, that's 1. So that's 1. What about the second part? So what's the limit as x approaches 0 of sine of x? Okay, so think of the unit circle at 0. What's your sine value? That value is 0. Therefore, my answer is 0. 1 times 0 is 0. So with limits, you're allowed to break it into parts. And so in this case, we're breaking it into parts that are multiplied, but if the parts are multiplied, then you multiply the results. If the parts are added, you add the results. If they're subtracted, you subtract the results. So all the basic operations we have, multiplication, addition, subtraction, you are allowed to break, when you're doing limits, you're allowed to break it into whatever you're looking at into several parts. And whatever operations you have between them, then you do that same operation with the limits. So again, so the limit of this is 1, the limit of this is 0, they're multiplied, so 1 times 0 is 0. Good. So what this also means though, is just, I mean, you just have, again, you have to go back to your pre-cal knowledge and just remember some basic things about your trig ratios and maybe some of your trig identities too. Yeah, that just kind of gets us about everywhere we need to go. So it's in terms of, especially in terms of discontinuities, this actually covers everything. So from that, you've got all the problems that you're going to see not only out of this section, but out of all 4 of these sections. So when they're asking you to find limits and you are having to actually plug things in and do it out correctly, again, either your function is continuous, or at least it's continuous within the domain, or the number they're asking you to take the limit of is again within where that function is continuous, even if it's some weird combination of functions. Again, once you know it's continuous, you just get to plug it in. If you know it's not continuous, then it's going to be one of these 3 situations I just showed you. It's going to be a rational, at least the ones that they major on here. It's going to be a rational function where you got to do factoring, or it's going to be a square root function where you got to rationalize the denominator or numerator, or it's going to be one of these special, it's going to involve one of these special limits. Just break it apart into pieces until you can find the limit of each part and then work it from there. You're also going to see some composition of functions, which works the same. If you know the limit of each part of the functions that are being composed, then you just close them and you get your answer. Anyways, yeah, so that covers everything for you guys. So that'll get you all 4 of these sections, 2.2, 2.3, 2.4, and 2.5. Go ahead and knock those through. I'm done by Sunday night. And I will see you guys next week with, so for y'all's class, yeah, I'll see you guys next week with some lectures on the derivative, the idea of the derivative, and then how to find the derivative. See you guys then.